Hey everybody, welcome to another episode of Robo Papers. Super glad to have with us Yan Jie from Stanford and presenting his paper called Twist, Teleoperated Whole Body Imitation System. Welcome to the show, Yan Jie.
Yeah, thank you. Thank you, Michael and Chris, for the invitation.
Yeah, so maybe as a start, if you could share about yourself, how you get into this kind of research.
So let me give a brief introduction of myself. So I'm Yan Jie. I'm currently the first year PhD student at Stanford, working mainly on robotics and kind of using the learning techniques to solve some essential robot problem. So now I'm focusing on addressing the whole body control and the whole body manipulation problem of humanoid robots. Yeah, so what I do in Twist, the teleoperated whole body imitation system, is that I try to use human data as a source of very, very powerful source for humanoid robot, really actuate the human robot to interact with this complex environment. So I think one interesting motivation of this work, as I said in actually a lot of works, is that I believe human data is very powerful, but now whole body iteration is not so mature to really leverage this power. So we can see a lot of recent works that are trying to do whole body control, like maybe 1 year ago, 2 years ago, there are some works like Human Plus and maybe some works from CMU that is achieved by Taiwan. And they actually show some impressive results that if you just using human data to control the human robot to control the upper body and lower body at the same time, you can do locomotion, you can do some squatting, you can do some jumping, but that's still before the twist, I think the scale showed by human robots by this whole body therapy system is still quite limited. So what is limited? What is limitation? I mean is that you cannot see very coordinated whole body skill. The human actually, you can kick the box. You can at the same time when you're holding something, when you open the door, and when you can, you can squat down very deeply to actually grasp something on the ground with your entire body. And at the same time, you can still maintain balance. Also, actually, at the same time, you can even reach out your feet to do something. So also, it's not just feet. You can also use the knees, use the shoulders, use your elbows, use every part of your body. You can use the head to do everything. Maybe previous people, they might use very complex techniques. You can define the contact. You can make the robot to track the contact, or you can make the robot to track the key point to achieve these kind of things. But it turns out that if we just use human data readily, if we just obtain accurate human data and try to transfer the human data entirely to a human robot without any loss of information. So that means each part of the human body should be mapped correctly to the human robot. If we can do that, we actually get this human level whole body dexterity onto the humanoid robot. So that is one thing I always want to do, and I'm very glad that we kind of achieve part of that in Twist.
Yep.
So let us see some video first. Yeah. So I think this is me doing some dancing randomly. Yeah. So I think this is a video that the humanoid is trying to clean up the chair, tidy up the chair after the human sits, slightly crouched down. Yeah, there's some other cool things like deeply crouched down to operate a garbage can and using another hand to lift it up. And now doing a backward work and close the door and tie the door.
Before Twist, there's no whole body teleoperation that can do exactly that, right? Basically, both lower body and upper body full
I think so. I think there's a lot of concurrent work and old works that can do this separately. So I think there's a recent work, maybe I don't know whether I can show here, is that from Xiaolong School. This is also very, very cool. So I think they show some similar skills, right? You can see our body very coordinated and it can grasp things. But for the comparison, you do not see some very flexible lower body movement at the same time, right? So I think basically they adopt the hierarchical framework to control the upper body and lower body separately.
Right, you can tell because they're not tracking the legs at all. They're just using a headset.
Oh yeah, they use VR headset to track the upper body, and the lower body is hard to obtain from only the VR headset.
So in this case,
so in your case, you can literally do some crazy yoga pose. Yeah, I suppose. Basically, it's a full body cut.
Basically, we can do anything. So you can just tell me what you most want to see from the human robot, and I can try. So now we already have some video to humanoid pipeline. So to extract the human pose from videos and to transfer this to humanoid. So we can also try just whatever you want. You can even send me a video of your you doing something and let me reproduce into onto the human robot.
Yeah, you have it like kicking a ball at some point, right? Because I think
So you
Yeah.
kick the box.
kicking something. Yeah, kicking a ball. Because I think
Well,
it's pretty impressive to me that you can do this in the same framework. Because, like you're saying, like most of these don't allow for the lower body control at the same time. Or this
Yeah.
one, that one with the feet is really nice, where it's holding something and then nudges something with its foot. Very capable motion.
That's true. Yeah, that's true. Actually, before we develop twist, I don't know. I don't expect such skill. You know, I don't expect like we kick something before doing this twist framework. I just expect that you can imitate all the bodies from humans. But it turns out that it's just a side effect if we develop a very powerful framework that can imitate all the bodies of humanoid, like some interest-driven short. Yeah. Anyway, so yeah, I think basically that's that twist. And so to achieve this, we just design a very simple pipeline, but we just make each pipeline very tightly connected to each other. So I think different to previous work, we use a mocap suit to collect the human data instead of using some very poor like egocentric pulse estimation or like monocular pulse estimation or like VR headset. All these kind of things now does not support quite well on the whole body estimation. Yeah, I think that's kind of the one of the key to really reach the upper bound of the whole body teleporting system. Yeah, and after this, we may think about how to make this system more portable, like how to use VR to extract the whole body, or like how to use camera, how to use egocentric video to extract whole body. But that's all should be done after we have twist.
Where does the large-scale human internet data come from?
Again, sorry.
In this plot, like you have large-scale human internet data. What is that? What kind of data is that? Where does it come from?
So this large-scale data is, I think, it's mainly from two sources. One is called AMAS and another is called OMOMO. So I don't think there are internet human data, but maybe this terminology is not so true. So AMAS is a very mature human data that is a collection, a bunch of different sources from is from Michael Black's group, and OMOMO is another collected data set with focus on human object interaction. So we combine them into one mixed data set to make sure like our humanoid can do all the kind of basic movements and also focus on the local manipulation things.
Just to get an idea of how much data is necessary, like how big are these? How big does the data set end up being?
It's around 50K motion clips, and the totaling is I think it's about like 60 hours maybe.
Okay.
Yeah, 6 hours of human motions. Yeah.
And how much of that?
And
how
are
much
these also
do you need?
track? I'm sorry.
Oh, I was just going to ask how much of your own data you needed, because you also say you have this small scale, which I assume is like helping map to the actual.
Yeah, I think it's like 1,000 of compared to the large scale one we use, 150 clips. Yeah, so like for internet that we used like 50,000, and yeah,
So very
something like that.
Yeah, so like this is 150
very
is like a day's worth of data, basically. Is that right? Is that kind of?
Yeah, we just use a very small scale. So I think there are a lot of reasons for we do not collect more, but the main reason is just collecting more is too much tiring.
Yeah.
So maybe we can collect more in the future.
So I guess your online retargeter with this like 150 clips is specific to actually what you have in the lab. So that helps you basically make it at least like retarget a lot better to the actual one that you guys use in your lab. Right. Okay, got it.
Yeah. So you mean the offline retargeting and online retargeting here?
Yeah, that's right.
Yeah. So there's kind of a trade-off between the offline retargeting and the online retargeting if you want to have very good performance. For example, during the online, you can actually have a lot of optimization iteration steps to get a very smooth strategy. But during online, you should limit the optimization steps to get a very good feedback, very good timely and accurately retarget. So in this work, we actually have two kinds of retargeting, like here, like offline or online, as I say. Yeah, and we try the online retargeting in the offline stage, but it does not work quite well since it's not so like carefully optimized. And also we try offline retargeting on the online stage, but since it is too slow, it cannot stop the online process. So that's why we have two here. And then we try to kind of mitigate the gap between them. It's not so large, but the gap is still not so neglected.
So I guess if someone else were to reproduce this result in their own lab, they just in theory need to collect maybe another 150 clips of small scale mocap and train specific to their whatever specific mocap environment they have in their lab.
Yeah, so that's a good point. So regarding to the reproducibility of this work, actually now it's definitely very reproducible. Actually, I don't think it's even necessary to recreate some data. You can just try the controller trained bio framework and maybe zero-shot deploy to the human robot if you are using G1, right? But in the future, I do think using the mocap is kind of increase this cost on the reproducibility and also increase the cost of the how people can use it. I don't think a lot of people can know how to correctly use a mocap since
it's a big
it's not
setup.
so complex setup compared to the VR setup. So we are considering maybe to find some portable solutions to replace this part. It's also possible, but there's trade-off that we may reduce the accurate tracking of the whole body, like the feet toe, the elbow, all these things.
Yeah. And I saw in your paper that I guess in your stage 2 here, you talk about a teacher policy and a student policy. I don't know whether this is the right time to go through that, but yeah, if you can speak to that a little bit.
You mean the teacher-student framework?
Mm-hmm.
Okay, so yeah, that's also actually a very essential design we have.
Mm-hmm.
So I think before talking to this, I need to talk about the formulation of this work. So we try to frame the whole body iteration framework as some tracking problem. That is, in each frame, your policy try to track one frame from the human. So that means what I show here is student only get the current time tracking frames from the retargeter. But that cause a problem is that since the policy cannot see the future, it will always cause some very unstable feed sliding behavior and also actually not so accurate since it's just because you don't see the feature. And if you are doing some quick walking or doing some running and you just receive current time step, you may have some conservative behavior since you want to make sure in the future you are safe. It's something like that. So, but actually in simulation, we have the access to a lot of previous information, including the future observation, future motion observation, also some other previous information like the gravity or something, the friction, all these things. So commonly done in Lego robot, we design a teacher-student framework to try to distill the previous information into the student by this teacher-student framework.
And I saw in the paper you say when you say future is something like, was it 2 seconds? Is it something like that? Into the future?
So since we are running inference at 50 hertz, and in each second there are 50 frames, and 2 seconds is 100 frames. So you can imagine that would be a quite large a large concatenation if we just direct connect all the future frames. So I think we do a very sparse sampling. We use future 1 step, future 2 step, future 5 step, and kind of concatenate 20 steps here. So that's why there are 20 here. Yeah. It's sample 20 steps in the future is 2 seconds.
Yeah. And I guess you also mentioned, I think you have a bunch of comparison where it's just RL versus RL plus behavioral cloning.
Yeah,
it's also
let me show the result here. So you mean some figure here and some curve here, right? So yeah. So in this work, we mainly compare some baseline we implement ourselves. So yeah, I think since this is more system work, so and also there are no too much comparable system as this system, so we need to design some baseline ourselves, right? So the baseline we design here is the Dagger and RL. It's more like the variant of our own final method. So our final is RL plus BC plus our own data is here, our mocap data. So if we remove BC part, remove the teacher distillation part, is then just single stage RL. If we not use RL reward to supervise the student, but we only use the action, kind of the MSE laws to supervise the student, then it's called Dagger. And I think some finding is that the Dagger, though it can maybe work well for some in-domain motions, but it cannot generalize quite well for the out-domain motion, like mocap or all the real-world data is quite noisy and it's very different from the data we collect. So I think if we are focusing on this task, reward-based learning is quite much better than this BC supervised learning. Yeah. So for evaluation, what I show the later figure here is that we collect another 50 motions individually as a test set instead of using some data sampled from our trained data set. So that ensures this fair this comparison is very fair. So this also simulates what's happening in the real world is that you don't know what's happening, and every motion might be different from the training data set. You just need to randomly collect some data and to see what's happening. And this is what will happen if, as I show here. So I think the best one is our RSIBC pipeline, our plus BC pipeline, and the worst one, I think the worst two are the Dagger and the RBC without the mockup data. And another interesting is that I think RO is quite competitive without the teacher-student distillation. But as I say, if you just use pure RO, you will introduce a lot of artifacts on the policy behavior that will make your policy look not so smooth. But you can definitely use that to do some tasks.
Did you do any? Did you do an ablation without the internet scale data and just with the mocap data?
That's a good question. So since I assume that the policy cannot track all the motions if we just had a very small scale of 100 motion clips, so we do not do that.
Okay, so you think it just would do really poorly. That makes sense. Okay.
Yeah. So our first stage will first train a general tracker that can basically track a lot of motions. So actually, I don't expect it can learn such a good controller from just 100 motion clips.
Yeah, that makes sense.
Okay, yeah. Also, there's some actually study here to show which part is the most error accumulated part. So I don't think this is very surprising. So basically, the finding here is that we find the end factor. What's the end factor is that the factors that actually do some functionality, right? Like the feet tall, like all the hand. You can find the error there is much bigger, much larger compared to some other parts. So I think it's understandable because you can view human as the tree, and your root and factor is at the end of the tree is the node, the leaf node, and the arrow is accumulated across this tree.
The root here is not the feet though; it's like the torso joint. You think that's the most accurate? Is that right? Yeah.
So I think basically the torso is the most accurate one. Also here a head since G1's head is stick to the torso, so you can just view the head arrow as some part of the torso arrow.
Makes sense.
And you have this kind of table that shows the observed latency. I think it's about 0.9 seconds, but then you also break it down some part of it is due to tracking. Could you talk about that? I find it a bit surprising that actually the first stage, the retargeting, take the most time. Actually, the robot, once you have it, it's actually quite fast.
Yeah, I think that's a very good question. So the truth is that now we have improved this part, and maybe later I would get you some more videos to show a very adaptive and low latency iteration framework. But I think at this time when we release, it still really has the 0.5 seconds delay between the streaming pipeline. So I would say here is more like engineering improvement. Now we do it in a very low latency. Yeah,
and
now
you basically just
0.1 seconds.
Oh, you mean the whole thing? The whole sec? 0.1 second?
Yeah, I think so. Or maybe lower than 0.1 second.
Oh, that's amazing. That will really feel like basically the human probably can't detect.
Yeah, that's right. The human will really cannot feel the delay now. Maybe we will get some new videos.
And that is
that's very impressive. I'm sure that allows for more complex tasks too, because the teleoperator isn't suffering with it.
Yeah, because once you have latency, the human will overcompensate for that, and then everything becomes a lot slower.
Yeah, that's right. That's definitely a very good question. Yeah, so if you try iteration, if the operator should compensate for the latency. That's true.
What was the trick to speeding it up that much?
Yeah, that's right. So that's why we act very slowly in a video, but now we can act much quicker.
What did you do to get it so much faster? Is it just lots of good engineering?
Maybe kind of fixing some bugs and doing some improvement. And I think no matter you're doing improvement or it's basically the same, you find the bottleneck of the system and you try to dive into what's happening and you find that majority part takes the most latency, cause the most latency, and you solve that part. And
this is running at was it a 4090 at inference?
Yeah. Okay. So I think for positive inference is quite fast. So usually it's just a MLP. It can run CPU or run GPU both in more than 50 Hertz. And for the retargeting, I think we are now also running on CPU. And yeah, I think finally this entire Teleoperated framework can be just deployed on board on the G1's onboarding computing. And now we are just doing it on our own workstation.
Got it.
For simplicity, that makes sense.
Yeah. Also, I think you just mentioned the failure case here, right? The falling down, overheating thing. Yeah.
Mhm.
I think this is I think the main bottleneck of our entire system to stop us to do very long and very smooth teleoperation. So since we usually, as you see on the left side, you cross down to do something very risky, and also you want to do some kick, that will, I think at some certain point, your torque will be very large, and that will cause a very large current onto your motor, and maybe at that moment, the motor is overheated and then it will suddenly fall down. I still think that's mainly the hardware issue that the Unitree people should try to fix. Anyway.
No, but in effect, it's like the humanoid doesn't have a body that is as reliable and maybe as strong. So while the humans can do it, maybe just is bounded by the hardware.
Yeah. So I think it's bounded by hardware, and also it's basically the different structure between like human and humanoid, right? So human is more like a tendon-driven system, muscle skeleton structure, and while now the mainstream of the human robot is like the actuator-based.
Yeah, actuators at the
motors.
joints.
Yeah. So I think it's the good part is that this system is more decoupled and simple to replace each part. But the bad part is that you have a very high requirement and you put a lot of payload to your motors, and your motor need to be very good.
Yep.
Yeah. It's
basically the angular momentum, right? At each of the joint.
Yeah, that's true.
Yeah. The other thing I was wondering, like, what if the human, I guess, teleoperator is just very, very different body, like, someone who's very tall versus someone very short.
Oh,
how do you think your system address that?
That's a good point. Our system can address that because we do a retargeting. So during the retargeting step, we just address this human embodiment gap. You can imagine that the mocap system can output the similar thing, but maybe with different limb length, different height or something.
Mhm.
And then we just retarget it to the humanoid with our system. To the robot. I don't think there's too much difference since it's a teleoperation. So I would say there's a lot of difference if it's like video-based learning. Since for each human, you need to have a different maybe adjustment for your policy to learn from that. So, but since it's teleoperation, you can do real-time feedback. You can adjust it if it's not so correctly, like to put their feet or like reach their target position. You can adjust immediately. Yeah. So generally, I think this like human embodiment gap is addressed by the mocap suit itself, and then the retargeting, and also the feedback system, like the iteration. Yeah, but that's also very good problem. Maybe in the future we should like invite 10 different users, like fat to tall, high to tall, like fat to thin, to experience, to see, to show that our system is quite robust to different users.
Do you think you need to do, like, if you had 10 different users, would you need to have 10 different mocap sessions for now? Or I guess eventually maybe you wouldn't need to do that? For the mocap data that you train on, the small portion, right?
Yeah. Yeah, that part is not so necessary, but it will. Actually, no, I would say that part is very necessary if you want to get real world good performance and you want to make it work. I think that's one morning that I think about what about adding some real world data into this training pipeline, and then magically like every component working so well after I add this small data. So you can imagine before this, our real world controller is very jittery when you consuming some real world data. The human is maybe hesitating their behavior, and because the robot lower body is not so robust. I don't know why it's jittering. Maybe it's just because of the domain gap. Yeah, and I think after this small kind of data set, every demo we show would be much more robust and smooth.
Yeah, but I guess I was curious if you thought you would need to add, like, because it was all collected by you basically. Do you think you'd need to collect like a wider range of people in the future to get that to work well, or do you think basically because of the retargeting step, it doesn't really matter and it's really just the data, the data, like what you have?
Yeah, the both matters. How you acquire the human data and how you retarget. And in the future, I think my next step will be definitely to scale up this data source to see what's happening. Since now you can see the most of the skills are like local manipulation. So, but I think human definitely have a lot of other corner skills. So, for example, a friend of me like told me to do some humanoid crawling on the ground. I actually tried that and it has not worked well because we actually don't have that much crawling data in the human motion. Yeah, and maybe, but it can be also very collected by humans and also some other like sit down. Like I don't mean sit on the chair. I mean just directly sit on the ground from sitting standard like behavior to sit down directly on the ground, something like that.
Yeah, Yanjie, I think you also mentioned in your paper you guys did something during the training to add some perturbation so that it can handle like holding an object. Could you talk us through a little bit how you do that?
Yeah, that's also a very good question. So I think a lot of previous like similar terrain systems that are trying to train a learning-based controller to handle this by like tracking human body, they all actually neglect the part to apply force. So I think it's mainly because previous system just use a gripper or use intellectual hand to do a grasping. But if you really want to, hold a box, you are giving the box a force, but without changing the pose of any factor.
Mhm.
If your policy is not trained with that kind of data, the policies become very unstable and you don't know what happened next time step, and the policy is confusing. So I think in this work, we just simply address that by adding some random perturbation on the end factor. Like we apply some random force like 16 Newton or something to make the robot learning simulation to know there's some random force on the end factor, and then it will better to give the force. So from my understanding, since our low level controller is like a position controller, so it just command robot to reach the target position. So you do not command robot to give us what kind of force it can give. So the robot need to learn to reach the target position, but without reaching the target position by applying the force. So that's the thing you need to learn.
So I suppose, what is the experience like for the teleoperator? I think you have a video where you literally have a big box, and then I think the humanoid use both arms clapping together and lift up the box, right?
Mention this one. This one.
Yeah, something like that. So when you were doing it, like how does it feel? Like do you feel? I mean, it looks like you have to close your own hands pretty close together.
Yeah. So the real experience that I don't know whether the robot can grasp the box, right? Since I don't know have the feedback from the robot, I only know it looks like it is grasping, but I don't know the real force it gives to the box. So that's why I try to close my hand as close as possible to make sure this. Yeah. The fatal case is that usually we cannot to truly hold the box very tightly. I think you can tell from this video because our hand do not have very like specific design for like a flat or maybe very frictional like surface. So sometimes it's just flat out from the hand.
And I suppose from your perspective, as in you, when you're doing this teleoperation, there's probably a fair bit of occlusion, right? Like literally the humanoid is blocking you. Yeah, you can't really tell whether you're lifting up the box.
Yeah. I think that's the bottleneck of the third person view teleoperation. So there are also a kind of line of works that doing like egocentric teleoperation, also like what I do in my previous humanoid manipulation project. And also I think it's mainly done by Xiaolong's student Xu Xing doing open television, and also recently use AM also doing egocentric teleoperation. Yeah. I think both of them have very clear pros and cons. So I tried the third person view teleoperation and egocentric both. So for third person view, the pro thing is that you can very clearly see everything what's happening, and except the visual occlusion. But except the visual occlusion, every other thing is very clear. But for the egocentric teleoperation, you only see the robot see. So that means if the robot does not have the eyes that's similar to human, so now I think mainly is the cameras mounted on the robot that is not similar to the human eyes. So that makes your view is quite limited. You only see maybe part of the human robot. So I think that's why the AMO paper, they add a neck on the robot to increase the view. So otherwise it just makes no sense. You cannot see basically anything. So yeah. So I would say that design is very good. So maybe in the future, I don't know whether we can add the neck on the G1, or maybe I hope Unity can add the neck on G1 for us.
Well, you could also do like a virtual third-person view, right? You could use the LiDAR and all to put a point cloud and the forward kinematics for the robot. Like make it easier so that you don't need to actually show the camera feed. That would probably so that way you wouldn't have self-occlusion at least.
Yeah, that's a good point. That's good. So how to really to see the robot see and how to do this entire teleportation, I think is still quite far away from like now. So now basically we are just build a whole body mapping, but how we improve this user experiments, right? I think it's a long way to go. I think one of my friends called Hao Yu, they're like from Stanford Shuran's group. I don't know whether you meet them, but they are doing some similar things. They're trying to really improve this egocentric teleportation system to make the users to be better to control the robot by using VR things.
Yeah.
But I would say there are a lot of things can be improved to really improve the teleportation. Yeah, it's still a very long way to go.
Yeah, that makes sense because
it's
it's not
not
a very
just
challenging way to
like
operate a robot by like watching it.
Yeah. That's very challenging. Yeah.
Well, very cool.
Is there anything that was surprising to you that this whole body, when you were doing this, that your system can do, or also cannot do? Like anything that you expected it to be able to do and just turned out to be way more difficult, or the other way around?
So the truth is, like, there already something that I maybe out of my expectation, especially the leg part, the leg manipulation, and but yeah, like this one, very large kick. I don't know, like we're deliberately to design this motion, but we just try this and it works. Yeah, it's like it's not expected behavior, but it works. And some other thing is that actually we do not try very risky one on the robot because we are afraid that it will break. And so, but maybe this one is a little risky. I don't know where you see. So we're trying to keep balance. I think just now you mentioned a paper called HUB, right? So they are doing very good balancing. So this is one trial. We try to make the robot to simulate it to balance with just 1 feet. So, but now it cannot. It can like lift for a while and then drop down to the ground to keep the balancing. Yeah. So, but I don't think this is a limitation on the pipeline. So it's still the data. We do not feed a lot of like balancing data in the training pipeline. So now it's basically local manipulation thing. So yeah, you guys can expect we can like have some calibration balancing at the same time in the future.
So in theory, if you get another like a big data set like Amex that has those kind of data.
Yeah.
And sorry, so those are those also like very similar kind of mocap data? Also using OptiTrack, that kind of thing. Okay, got it.
Yeah, I think so. I think all this like the high quality human motion data is captured by this motion capture system that is also widely commercialized. But now the third person view based, like video based full body pose estimation also become very mature, and
yeah,
you only need to do some. Yeah, I would say they are already very good, very good. Yeah. But though not as good as the mocap, but it's very close to the use.
Yeah, because if you can just fit in video, there's so many human video on YouTube. That's just way bigger source, right? So if you can go look past the fidelity, but then you have just so much more. So that can give you all the like whatever human pose you can find, probably.
Yeah, that's right.
Somewhere.
Yeah, I think that's also one motivation of like video mimic. They try to like using internet human video to do something. But though it turns out finally they now achieve is like using the in-house like self video shoot by themselves to do something. But I believe in the future they may extend to the internet. Yeah, and also for our work, I will try to extend to the large scale internet video data.
That's awesome. Very cool. Yeah, Chris, do you have more questions?
I think it's a great explanation. Very cool work. Do you want to ask our wrap-up questions, Michael?
Oh yeah, so usually like to wrap things up, like usually we will ask like, is there any like other cool papers that you come across? But actually, just how you already mentioned a few other papers. Anything else that kind of pique your interest? Doesn't have to be like humanoid whole body control, that kind of thing.
You mean like recent interesting paper, or or just any paper that from any time?
Yeah, could be. Yeah, good. Doesn't have to be recent, honestly. Yeah, any paper that you want to just give a shout out to.
Could you guys give a more specific direction so that I can quickly
No,
come
it's
up
like
with a
what was
Yeah.
the last paper you read that you thought was really cool? I guess like that you
Okay,
wish you'd
so
written, maybe. Let's say.
let me just check my paper list. Okay. Yeah, I think maybe just let's say among these recent like released like humanoid
Mhm.
papers, right? So I would say I would shout out to this video mimic.
Mm.
Yeah.
Mm.
Yeah. I would not I would say the pipeline or the other techniques are very good, but I really like their videos. The quality of the video, the color or the background, you know, all the entire things, the website design. Yeah, really. You can tell a lot of like effort are put into all these visually cool things.
Mm.
I really need to learn a lot from this, how they shoot the video. Yeah,
Yeah.
it's very like beautiful, cool, and have a technique combined with the humanity, some kind of the human are watching, trying to climb up the stairs. Yeah, I really like this paper. Though I think though they do not have show like some object interactability now, it's just mainly the locomotion, and also it's mainly the skills. So the show is not that diverse, but there are a lot of potential in this pipeline, right? The real to sim to real, the object interaction part.
Definitely. Yeah.
Anyway, the favorite part from this paper still is the video.
Yeah, really cool. I think we're speaking with Arthur, I think a couple of weeks time. So yeah.
Oh,
Yeah.
that's
So
cool.
give a shout out to him.
Yeah.
Yeah.
Okay, very cool. Well, anyway, thanks so much for showing up, Yanjie. I thought it was super cool. Like when I saw your paper, I was like,
Yeah.
as you
thank
know,
you.
I'm doing this robotic gaming thing with the fighting.
Yeah.
I think it's always like the thing I'm personally interested in is the actually it's more from the human perspective. Like that's why a couple of the questions I asked you just now is related to how the human teleoperator feels.
Mm.
I mean, ultimately, if we're talking about getting human data in real time, like it matters a lot what the human feel. You know, things like
That's true.
occlusion, like feedback. So, because in theory, the more enjoyable and more tolerable, let's say, or maybe even fun the experience will be, then the more that particular human can keep giving you data, right? Because he
Yeah.
doesn't feel that it's a chore, right?
Yeah, that's true. Yeah, that's a work one. Yeah, I definitely agree with that. That's also the one goal I want to achieve, that is terrorizing without any pain. But now,
Yeah.
to be honest, it's so painful to wear the mocap suit to do the terrorization.
Yeah, I can imagine. But I would say a big step is also just reducing the inference latency. So 0.1 second is super good. I think that's a huge part of the whole UX actually.
Yeah, I would
Yeah.
expect to show the videos maybe in next few weeks with the low
Okay.
latency and maybe to do more quotas. Yeah, let's see.
Yeah, that sounds great.
Okay. That's awesome.
Awesome.
All right. Thank you so much, man.
Thank you.
All right.
Yes.
Thanks for
Yeah,
coming
thank you for
on.
the invitation, Michael and Chris.
Yep.
Thank you.
Yeah.
Cool. Okay, cool. Chris, what do you learn?
Yeah, I mean, I really like this work. I think that, I guess to learn that you can do this, right? Like that's what my takeaway was, and I was super impressed. Like I said during when we were talking, but like I was super impressed by the kicking, like particularly the one where you carry the box and nudge something with your foot, or like kicking a soccer ball, just because like that's really hard, and because like it's got to balance, it's got to move its leg, it's got to do something with the arm, and it's just like super impressive work. It looks like there's a lot of I think that the student teacher setup that he had, and particularly the co-training on like some amount of mocap data and the web scale data, all this, like lots of cool details. What did you think?
Yeah, I thought it's like you say, it's probably this is the first one I've seen. Having said that, during that 1-2 weeks, a lot of like whole body, like humanoid controller
They're all
all come
different
out around
though.
the same time.
They all do things slightly.
Yeah,
differently.
it's true. It's
Yeah.
true. Yeah,
They're all
but this
showing.
particular one, I would say, it's impressive to me in that like because he is really a full body capture, right? So he can do tasks that truly involve like both like lower body and upper body. Because most of the other ones that I've seen usually it's a lot more like details on the upper body, and then the lower body is just to do balancing and not fall, right?
Yeah, right.
Whereas in this case, like I said, he could be holding something in the hand while shooting a ball, right? He can do that because it's full body.
Yeah.
And I do think the current pipeline obviously is starting from motion, the mocap, but mocap it's at least the way it's set up, it's very hard to scale. But I think we're probably getting to a point where just pure video like body pose estimation from just straight up video of human video is getting to be really maybe as good as some of these mocap data, then I think you have huge amount of data on YouTube
Yeah.
that you can just activate all kinds of poses. Yeah.
Right. Like I think what I think is really cool here is, not to belabor the point, but like this is what humanoids are for, right? Like a humanoid has legs, you should use the whole body, right? And that is,
Exactly.
I think, like this does that really, really well in a really evocative, like really cool way, I think. Yeah. So no,
Yeah.
it's cool stuff.
Yeah.
And yeah,
I think another
once
thing
you can
that
get that web data, you really can do some impressive things, I think, like you're saying.
yeah, for sure. And I think the other thing he was highlighting, which was quite interesting, is that the trade-off between like what do you say, like a third party view or versus
Yeah,
egocentric view, like
yeah.
basically two ways to kind of teleoperate, real world teleop, so real time teleop. And so yeah, it's I can see both having its own
Yeah.
trade-off.
This is
Yeah,
like
so
I
that's
don't
also
know, but
quite
this is
interesting.
actually something that we did back in grad school. It was like we had VR headset with like for industrial robots. Like this was way before humanoids because I'm old. But like you would have like a big industrial robot that you can't control, and then you'd have like a depth camera or something, so you could have you just have
Yeah.
a floating model of the robot and and the thing there, and you could see the point cloud. So like if the latency stuttered, everything would be fine, and then you could like you can grab the end effector and move it, or you can just move and control the robot. And like I think that they're basically, this is a long-winded way of saying I think this is a user interface problem, and I think you could totally solve it. Like you could get the best of both worlds. I think it just takes some engineering, right? Like, yeah. I just think about it a little,
I see.
right?
But personally, do you think like the egocentric way is because I mean we all move around the world in the egocentric. I mean our eyes is
I
our
don't
eyes.
think
So
egocentric makes much sense actually, no, because I think like
oh,
the way that
okay,
we do stuff is that we move our heads a lot,
Mhm.
right? Like so like
That's right. That's right.
my head is, if I as a robot, the robots don't have our necks usually, or like even if they do, they're not going to move like the way that we do. Like our eyes are always like
Yep.
well, I forget the word, but like they move
Yeah.
around to get like a lot of
Yep.
our structure, the 3D structure of the world that we as humans use is from our heads and bodies moving, and that's not going to be true for the robots ever, I think, or not like realistically for a good amount of time. Like you were saying, like EG1 is fixed, so like I think you need some compromise, and like, but yeah, I don't
And
know. Yeah.
so you think the compromise? So you think is a better compromise, to actually just kind of do exactly his setup, which is a third person view, right? You
Yeah,
are
but
just observing
I think a
the robot that
virtual
you are
third person view
controlling.
is better, because then you can do things like change the alpha of the robot. Like like if you can change the alpha of the robot and stand where the robot is and like just marionette it, like I think like that's the kind of thing that, like, again, we've done that kind of stuff before. Like, and I think that kind of approach makes a ton of sense, because then you get the best of both worlds, and like you can tell what the robot can see because you are seeing the sensor feed, and right, but like then your head is moving. Like you don't get that jarring disconnect between the real world and the simulation. I don't. Yeah, that's just my first feeling is it, because like I think his intuition that the third person view is better is I think that's correct, right? I think that like it's gonna be real. I think it's gonna be really hard to get a first person view to work well, but I don't know.
Got it.
Yeah.
Cool. Okay. Cool. Wow.
Cool. Anyway,
Great chat as
it's really
usual.
cool stuff. Yeah.
Yeah. Look into it.
Anyway,
Yeah.
see you next time.
Looking forward to the next one. Okay. Chat soon.